Good afternoon, friends. I am Mr. L.S. Thakur from ITM Universe, and today we will be covering up a topic known as truss. If we talk of a truss, what we will be covering today will be static determinacy of a plane truss, methods of analysis of truss, basically two methods, then what are zero force members, analysis of simple determinate plane trusses using method of joints. Now, if you know what is a truss, and before that we go into the definition of a truss. A truss is basically a structure comprising of one or more triangular units constructed using straight members whose ends are connected using a pin joint. If you see this figure, this is showing you a typical truss which is used for roadways. These joints shown here are basically comprising what is known as a pin joint or a node. The simple example of that can be taken up with your hand. Your elbow joint is basically a pin joint which can rotate about its axis but cannot not rotate about it. It can only move about that axis. If you look into the second definition of a truss is a structure composed of slender members joined together at the end points using a pin joint, and the loads are as shown in your figure. It is defined as a planar truss in the case when you have all the loads which are lying in the same plane of the construction of the truss. In that case, this is known as a planar truss, and if your loads are defined into directions which are perpendicular to that, then it is known as a again a truss only. What do you mean by a simple truss? What we will be solving today are determinate trusses. A simple truss is a planar truss which begins with a triangular element and can be expanded by adding two members and a joint. So if you see this figure basically has three members. Into this, if I add two more members, that is AD and DB, I am forming another triangle which is triangle ADB, and I am introducing one more joint at point D. So in this case, I have extended my truss by introducing two extra members, that is AD and DB, and putting in another joint which is joint D. If you want to check out whether your truss is a determinate truss or a simple truss, then we need to look into the equation, that is m is equal to 2j minus 3, where m is the number of members, j is the number of joints, and 3 is a constant which is with respect to the number of equations for equilibrium. Now if you see this case here, if you see A to C, that is member number 1, then you have BC, member number 2, and then AB, which is member number 3. So we have a total of 3 members, so m is equal to 3, and if we took into the number of joints, we have one joint at A, another joint at C, and another joint at B. So total number of joints is 3. So if you take out this equation, 2 into 3 minus 3 is equal to 3. So number of members m is equal to 2j minus 3. This equation is satisfied. That means this equation or this truss can be solved easily and is a determinate simple truss. We will be first looking into the sign conventions which we need to use when we are solving a truss. So your basic first is, if I am pushing my two hands one together the other, and I am pushing them like this, so I am pushing these hands together, so it is basically giving a compression force on my surface of my hand but giving a tension onto the joint which is the node. And similarly, when I pull my hands together, then it is giving me a tension and giving me a compression force on the joint. The sign convention used another way is this form, where you can see tension and compression in both the cases, and what is the effect on the joints will be seen in the next slide. If you see, this member in member 1 is a tension member but is giving an opposite force onto the joint shown in yellow, whereas if you see the joint member number 2 is under compression but giving an opposite force to the joint J. If we talk of the whole truss, and once we solve the truss, we can log out what are the number of forces in the members, the magnitude of the forces and the direction of the forces, as well as the type of force, whether it is a compression type of force or a tension type of force. So this figure is showing you these members under compression where C is written, and these members under tension where T is written. These are some of the common types of trusses which are used in day-to-day life, which you have as Pratt truss, Howe truss, and Fink truss, which are basically typically used for your roofs in your industrial sheds. Then you have Pratt truss, Howe truss, and Warren truss, which are used for bridges. Then you have Baltimore truss and K truss, which are again used for large bridges. Then you have a stadium truss, which is used for stadium constructions. Then you have a cantilever portion of a truss, again used when you want to extend your construction of a stadium. Then you have bascule truss, where you have movable trusses for bridges. This is the most common bridge which we have all seen, which is the Narmada bridge, which has now been closed for traffic and is only used for light vehicles. This is the oldest bridge. You can see it is constructed in 1877 and still standing. This is a typical construction of a steel iron bridge. Another bridge example which is used for two common purposes, that is transportation of pipeline as well as transportation of railway line, is your Mahi bridge, or what you know as the Vasad bridge, shown in the figure. Another view of that same thing is shown, where you are carrying on water from the same Vasad bridge and it is crossing over using a large number of trusses. This is a typical railway bridge, wherein you have the lower portion being decked up for the railway line to move, and two trusses are connected using connecting rods or connecting trusses. Again, you can see here these are connecting trusses again. So these are to be analyzed again as form of a truss only. This is another truss which has been used for a bridge over two supports. This is your famous Sydney Harbour bridge, where again a truss has been used, but the total members are curved in section and the bridge has a suspension edge section on which your roadway is moving. Then you use trusses basically for industrial purposes, for creating large spaces which are unhindered large spaces below, so that you can keep your work going on without any hindrance. So these are large trusses which are constructed. This is basically an N type of roof truss created for industrial shed. These are nowadays also used for restaurants, where you use basically wooden members to create a truss, and is shown in the figure. Trusses are also utilized for transmission towers. Here you can see a transmission tower which is being constructed by three different types of planes of trusses, and this is basically known as a space truss. If you see the front view of that same thing, you can see a truss being constructed in verticality. Trusses are also used for tower cranes and gantry cranes, as shown in your figure. This is a vertical truss, and you have a horizontal truss which is attached to the vertical truss, used to carry heavy loads over a large distance and height. Then you have gantry cranes which carry large loads. Again, you have a truss in the horizontal section and in the vertical section both, which you can see here. Now, if you talk of methods of truss solving, we have basically two methods of truss solving. One is method of joints, another is method of sections. Today we will be looking into method of joints first. Before we start on to the method of joints, we have to know what are the assumptions taken for a truss. If you talk of a truss, we have basically three basic assumptions taken. All members are straight and connected to each other by pin joints. That is, you do not consider any of the members to be a curved member, and they remain straight even when the loading has been applied. The second assumption is loads are applied only at the joints. That is, you are not applying a load at the center of the member, but it is being applied only at the joint of the members, wherever the members are matching each other or connecting to each other, and they are in the plane of the truss itself. This assumption is very much necessary, because we are solving a planar truss and not solving a space truss. If your loads are in the plane or perpendicular to the plane of the truss, then it becomes a problem of a space truss, which we are not going to cover. So all the loads are in the plane of the truss, and only then do I call it a planar truss. And the weight, third assumption is weight of the truss is negligible compared to the load applied on the truss. That is, if I call off the total load of the truss, which is being constructed out of steel, then the total load of that is negligible, and therefore we can neglect that load when we are considering the forces of the members to be found out. So what are the truss steps we need to follow when we want to analyze a truss? The first step is, if the truss supports are not given, that is, the support reactions are not given, then we need to first draw a free body diagram, which we have already gone through, of the entire truss and determine the support reactions, typically using your scalar equations of equilibrium, that is summation fx equal to 0, summation fy equal to 0, and the third equation is summation m equal to 0 at any point, or summation m equal to m on right hand side is equal to summation n on the left hand side. Once you have done that and found out your support reactions, then we need to draw the free body diagram of a joint with one or two unknowns. Not more than two unknowns are to be used, because in that case we will not be able to solve the equation, because we are considering it to be a coplanar concurrent force system where we have only two conditions of equilibrium, that is summation fx equal to 0 and summation fy equal to 0, or summation v equal to 0 and summation h equal to 0. Then assume that all the unknown members act in the tension force, that is all are moving away from the joint, is to be considered, unless until you can determine by visualization that the forces are under compression load. But if you are not sure, it is always better that you assume this to be under tension or going away from the pin joint, and then start solving your equations. Then we need to apply the scalar equations of equilibrium, that is summation fx equal to 0 or summation h equal to 0 and summation fy equal to 0 or summation v equal to 0 to determine the unknown forces or stresses in the members. If your answer is turning out to be positive, then it means that your actual member is under tension and your assumed direction is correct. Otherwise, the direction is to be reversed, that is your actual member is under compression where you have assumed it to be under tension. So you have to reverse your direction of the member and then solve the next joint considering the actual direction of the member and not the tension member. If you want to use the tension member or the tension sign, in that case it is necessary that you use the value of your force to be negative only. If you do not change the direction and use the value to be positive, then subsequent answers of all joints which you are solving will go wrong. Then once you have solved one of the joints, then you have to repeat the same points, that is point number 2 and 3 to each and every joint where you have maximum 2 number of unknown forces. Then the first most thing which comes into your mind when we are solving a truss is a zero force member. What is a typical zero force member? If a joint has only two non-collinear members and has no external load or is not having any support at that joint, then those members are known as zero force members. In this example, we can see force member number DE, member DC, member FA and member AB. All these are only joined at a point, that is A and D, have no external forces being applied and do not have any support reactions at that point. That means these members, that is member FA, then member AB, member ED and member DC, all of these are to be considered as zero force member. Now what do you mean by a zero force member? A zero force member is basically being put in only to increase the stability of your truss. It is not there to carry on or take any type of load onto itself. So even if I remove these members, that is member DE, member DC, member FA and member AB, in that case my truss will not change in its stability. So if you can see, if I remove these members, the truss becomes what is shown in the figure below. You can have another example of zero force members in this figure where you have support reactions at point A and B and force is being applied at point E. So if you see at joint D and joint C, member AD and member AC are not carrying any force or are not being supported, being used to support the truss. Again in this case, if I remove this member AD or remove member AC, then in that case the total stability of this truss will not be affected. So this becomes the case. Now zero force members are also used to increase the rigidity of the truss. Now if you see here, the truss is there, but if I have removed these two, this point E can move in case of a larger force being applied and the shape of this truss can change. So this is the case where we require the zero force members. Moving on to the actual method of joints. If I am to solve this simple truss which has only 3 members, the first thing that we need to look into is whether it is a statically determinate truss or not. Because this is in your course, these all members or all examples which I am solving are basically statically determinate trusses only. So I have at joint A a support and at another support at joint C, and at joint B I have a force of 500 Newton being applied in the direction from B onwards, going away from the point B. So if I draw a free body diagram of joint B, I get something of this sort, where I have FBC under compression and FBA under tension by common sense. Now what do I do when I want to solve such a truss? When using the method of joints to solve for trusses in a truss members, equilibrium of a joint pin, that is point B, is to be considered. All forces at that point B are to be drawn in your FBD, that is your free body diagram, including all the external forces, that is all support reactions, as well as external forces which are acting on the member, and then apply your equations of equilibrium, that is summation Fx equal to 0 and summation Fy equal to 0, and solve out for the unknown forces. I have already talked to you about this equation m is equal to 2j minus 3 in my second slide. Now we will be looking into what are the cases in this case. Your first case is m less than 2j minus 3, that is the number of members as per requirement is less than what is being given by 2j minus 3. In that case, your truss becomes unstable and will not sustain the applied load onto that truss. If I have m greater than 2j minus 3, that is the number of members are larger than what is required by the truss, then your truss becomes an indeterminate truss or becomes a redundant member, has a redundant member. If you have m equal to 2j minus 3, then your truss is a perfect determinate truss, which is there in your course, and we will be solving only such trusses. But you need to understand this equation for any further solving also. So if I look into these three cases, that is case A, B and C, and if I want to solve them, if I talk of truss A, then I have how many number of members? See, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So m is equal to 9. Then I have j, that is number of joints, 1, 2, 3, 4, 5 and 6 number of joints. So if I talk of m equal to 2j minus 3, it is being satisfied and the truss is called to be a statically determinate and stable truss. If I talk of the second truss, that is shown in figure B, then I have number of members equal to 1, 2, 3, 4, 5 and 6 members, and the number of joints is 1, 2, 3, 4 and 5. This is not to be considered as a joint because only the members are crisscrossing and it is not joined at that point, so it is not considered as a joint. So you have total 5 number of joints, 3 number of reactions. So the equation is m is less than